Hello, dear traveler. Welcome back to the Midnight Explorer, where we wander through the twilight hours together, exploring the stories that shaped our world. Stories whispered in laboratories late at night, stories written in equations that changed everything we thought we knew about reality itself. Tonight, as the world outside grows quiet, I want to take you on a different kind of journey. Not across oceans or through ancient kingdoms, but deeper. Down into the very fabric of existence. Into a realm so strange, so beautiful, so utterly mysterious that even now, more than a century after its discovery, it continues to perplex and astonish the greatest minds who dare to explore it. Tonight, we're going to talk about quantum physics. But don't worry, this isn't a lecture. There are no tests, no formulas to memorize, no right or wrong answers. This is a bedtime story. A story about human beings who looked at the universe and saw something impossible. Something that shouldn't exist according to everything we knew about reality. And yet, it did exist. It does exist. Right now. In this very moment, in the atoms that make up your body, in the light reaching your eyes, in the screen before you. So settle in. Get comfortable. Let the day's worries fade away. And let me tell you a story about the night the universe revealed its deepest secret. Let's begin. Close your eyes for a moment and imagine the world as it was understood in the year 1899. Picture a scientist, perhaps standing in a grand university hall in Berlin or Cambridge. The gaslight flickers against wooden panels. Through tall windows, the stars shine with what seems like perfect clarity. Everything in the universe, this scientist believes, has been explained, or will be very soon. The universe is a magnificent clock. Every gear, every spring, every pendulum swinging in perfect, predictable harmony. If you know where something is and how fast it's moving, you can predict exactly where it will be in the future, forever. The past determines the present determines the future. Cause and effect, flowing like a great river from the beginning of time to its end. Isaac Newton had given humanity the keys to this cosmic machine 2 centuries earlier. His laws of motion and gravity could predict the paths of planets, the fall of apples, the trajectory of cannonballs. They worked perfectly, consistently, beautifully. And then came James Clerk Maxwell, unifying electricity and magnetism into a single elegant theory. Light itself was revealed to be an electromagnetic wave, rippling through an invisible medium called the ether, which filled all of space like an ocean fills the seas. Everything was waves or particles, solid, understandable things. Waves in water, sound waves in air, light waves in the ether. Particles of matter, tiny billiard balls bouncing off each other according to Newton's laws. The universe was comprehensible, mechanical, knowable. Lord Kelvin, one of the most respected physicists of his age, supposedly said that there was nothing new to be discovered in physics. All that remained was to measure things more and more precisely, to add decimal places to the constants we'd already discovered. But even as he said this, there were cracks appearing in the foundation. Small things, annoying things, little problems that didn't quite fit. There was the problem of black body radiation. When you heat an object, it glows, first red, then orange, then white as it gets hotter. But according to the classical laws of physics, when you calculated how much light should be emitted at each color, the mathematics predicted something absurd. The equation said that any heated object should emit infinite amounts of ultraviolet light, and beyond. infinite energy, which obviously didn't happen. This was called the ultraviolet catastrophe, and no one could explain it. There was the photoelectric effect. Shine light on certain metals and electrons are knocked loose. But strangely, the color of the light mattered more than its brightness. Bright red light did nothing. Dim violet light freed electrons immediately. According to wave theory, brighter light should always produce stronger effects, but it didn't. There was the mystery of atomic spectra. When you heat different elements and look at their light through a prism, you don't see a smooth rainbow. You see specific colors, discrete colors. Hydrogen always produced the same pattern of lines, sodium a different pattern. But why? Why only certain colors, not a continuous spectrum? These were the small cracks in the foundation of physics. Most scientists thought they were minor problems, easily solved with a bit more work. They had no idea that these cracks were about to widen into chasms, that the foundation itself was about to crumble, that everything they thought they knew about reality was wrong. And the story begins, as so many stories do, with someone who couldn't sleep.
Picture Berlin in the winter of 1900. Snow falling softly on cobblestone streets. In a modest study, a man sits by lamplight, surrounded by papers covered in mathematics. His name is Max Planck, and he is a respectable, conservative physicist, 42 years old, distinguished, traditional. And he is desperate. For years, Planck has been wrestling with the black body radiation problem. It's become an obsession. The ultraviolet catastrophe haunts him. The mathematics keeps predicting infinity, and nature keeps proving the mathematics wrong. He's tried everything, every classical approach, every conventional method. Nothing works. And then, late one night, in an act of what he will later call desperation, he tries something different, something that makes no physical sense whatsoever. He makes an assumption, a wild assumption. What if energy isn't continuous? What if, instead of being able to have any value at all, energy can only come in discrete chunks, packets, little bundles? It's like imagining you can't pour any amount of water you want, but can only pour water in cupfuls. 1 cup, 2 cups, 3 cups. Never 1.5, never 2 3/4. Just whole numbers of cups. Planck calls these bundles of energy quanta, from the Latin word for how much. He works through the mathematics again with this bizarre assumption. And suddenly, miraculously, everything fits. The equation matches reality perfectly. The ultraviolet catastrophe disappears. The black body radiation curve is predicted exactly. He has solved the problem. But Planck is not happy. He's disturbed. Because he doesn't believe in quanta. He thinks they're just a mathematical trick, a useful fiction. Surely energy must really be continuous. It has to be. Anything else makes no sense. He will spend the next decade trying to get rid of quanta, trying to find a classical explanation. He never succeeds. Because quanta are real. On December 14th, 1900, Planck presents his findings to the German Physical Society. The date is later considered the birthday of quantum physics, though almost no one at the time realizes the significance of what has just happened. Planck has opened a door, just a crack, a sliver of light from another world shining through. And very soon, someone is going to push that door wide open. That someone is a young patent clerk in Switzerland, a man with wild hair and wilder ideas,
a man who will become the most famous scientist in the world. His name is Albert Einstein. Let me tell you about Albert Einstein in 1905. He's 26 years old. He works 6 days a week evaluating patent applications in Bern, Switzerland. It's not particularly exciting work, but it pays the bills. He's married to Mileva Maric, a fellow physicist. They have a young son. They live in a small apartment. And in his spare time, in the early mornings and late evenings and on Sundays, Einstein is rewriting physics. He works alone. He has no laboratory, no research grants, no prestigious university position. Just a desk, paper, a pen, and his mind. In this single year, 1905, he will publish 4 papers. Any one of them would have been enough to make him famous. Together, they will change our understanding of reality forever. This year will become known as Einstein's miracle year. One paper explains Brownian motion, providing final proof that atoms exist. Another paper introduces the special theory of relativity, showing that time and space are relative, not absolute. A third paper contains the most famous equation in physics, E equals mc squared, showing that mass and energy are interchangeable. But the first paper he publishes, in March of 1905, is about light. He reads about the photoelectric effect. He knows about Planck's quantum hypothesis, and he sees something that even Planck didn't see. Planck had suggested that matter might emit energy in quanta, but Einstein goes further. What if light itself is made of quanta? What if light isn't a continuous wave at all, but rather a stream of discrete particles, packets of energy, flying through space? He calls these particles light quanta. Later they'll be called photons. This is a radical idea, more radical than Planck's, because everyone knows light is a wave. Thomas Young had proven it with his famous double-slit experiment a century earlier. Light creates interference patterns just like waves in water. It diffracts around corners. It has wavelength and frequency. But Einstein proposes that light is also a particle. Each photon carries a specific quantum of energy determined by its frequency. High-frequency light, like ultraviolet, consists of high-energy photons. Low-frequency light, like red, consists of low-energy photons. This explains the photoelectric effect perfectly. When a photon hits a metal, it either has enough energy to knock an electron loose, or it doesn't. No amount of bright red light, many low-energy photons, will free an electron if each individual photon lacks sufficient energy. But dim violet light, fewer but higher energy photons, works immediately because each photon packs enough punch. It's not about the total amount of light, it's about the energy of individual photons. This explanation is so elegant, so perfect, that when Einstein eventually wins the Nobel Prize in 1921, it's for this work on the photoelectric effect, not for relativity. But there's a problem, a profound problem. Is light a wave or a particle? The answer, impossibly, appears to be both. And this is where the quantum mystery truly begins. This is where we step through the looking glass into a world where nothing makes sense according to our everyday experience, where reality itself becomes strange.
While Einstein is revolutionizing our understanding of light, across Europe another mystery is deepening, the mystery of the atom. By the early 1900s, scientists have discovered that atoms aren't indivisible, as the ancient Greeks believed. They're made of smaller parts. J.J. Thomson has discovered the electron, a tiny particle with negative charge. Ernest Rutherford has discovered the nucleus, a dense, positively charged core at the atom's center. Rutherford's model of the atom is like a miniature solar system, Electrons orbit the nucleus the way planets orbit the sun, held in their paths by the attraction between opposite charges. It's beautiful, elegant, and completely impossible. According to Maxwell's equations, an accelerating charged particle must emit electromagnetic radiation. An orbiting electron is constantly accelerating as it moves in a circle, so it should be constantly radiating energy, and as it loses energy, it should spiral inward, closer and closer to the nucleus. The mathematics says that every atom in the universe should collapse in about a trillionth of a second. But they don't, obviously. You exist. The world exists. Atoms are stable. Something is very wrong. Enter Niels Bohr, a young Danish physicist. In 1913, he's working in Rutherford's laboratory in England. He's thinking about hydrogen, the simplest atom, one proton, one electron. And Bohr makes a leap, a quantum leap, if you will. What if electrons can't orbit at any distance from the nucleus? What if, like Planck's energy quanta, there are only certain allowed orbits, specific distances, discrete levels, like rungs on a ladder? An electron can be on one rung or another, but never in between. And crucially, while an electron is on one of these allowed orbits, it doesn't radiate energy at all. The classical laws simply don't apply. To move from one orbit to another, an electron must absorb or emit a quantum of energy, a photon. And the energy of that photon corresponds exactly to the difference between the two orbital levels. This explains the spectral lines. When hydrogen is heated, electrons jump to higher orbits. When they fall back down, they emit photons. But since only specific orbital jumps are possible, only specific photon energies are emitted, and specific energies mean specific colors. Each element has its own unique pattern of allowed orbits, and therefore its own unique spectral fingerprint. Bohr's model works beautifully for hydrogen. It predicts the spectral lines with stunning accuracy, but it's deeply unsatisfying philosophically. Why are only certain orbits allowed? Bohr can't say. The model works, but no one understands why. And for more complex atoms with multiple electrons, the model doesn't work as well. It's incomplete. But Bohr has planted a seed. The idea that perhaps the atomic realm doesn't follow classical rules, that perhaps there's a different kind of physics at play. The quantum realm is revealing itself to be profoundly different from the everyday world, not just quantitatively, but qualitatively. It's not just smaller, it's stranger. And the strangeness is only beginning. Sometimes the most revolutionary ideas come from the most unexpected places. Louis de Broglie is a French prince. Yes, an actual prince from an aristocratic family. By all rights, he should be attending parties, managing estates, living a life of leisure. But Louis de Broglie loves physics. In 1924, he's working on his doctoral thesis, and he's thinking about Einstein's photons, about how light can be both wave and particle. And he wonders, if waves can behave like particles, can particles behave like waves? It seems absurd. A baseball doesn't spread out like a wave, an electron orbiting an atom doesn't ripple. Or does it? De Broglie proposes that every particle has a wavelength. The wavelength depends on the particle's momentum. For large objects like baseballs or people, the wavelength is so incredibly tiny that we never notice wave-like behavior. But for very small particles, like electrons, the wavelength becomes significant. He derives an equation, simple, elegant. The wavelength equals Planck's constant divided by momentum. And here's the beautiful thing. If electrons are waves, then Bohr's allowed orbits suddenly make sense. They're standing waves. Imagine a wave on a vibrating string. Only certain patterns are stable, certain harmonics where the wave fits perfectly around the orbit. Other patterns destructively interfere with themselves and disappear. If an electron is a wave, it can only orbit the nucleus at distances where the wave fits perfectly around the orbit, creating a standing wave. At other distances, the electron wave would interfere with itself and cancel out. The mysterious quantum rules aren't arbitrary after all. They're the natural consequence of wave behavior. De Broglie submits his thesis. His examining committee is skeptical. These ideas are so strange. They send the thesis to Einstein for his opinion. Einstein reads it and sees immediately that it's brilliant. Within 3 years, de Broglie's hypothesis is confirmed experimentally. Scientists fire electrons at crystals and observe diffraction patterns exactly like light passing through a diffraction grating. Electrons are waves. But wait, they're also particles. We can count them individually. We can measure their charge and mass. So, what are they really? The answer is going to turn out to be far stranger than anyone imagined, because we're about to discover that asking, "What is an electron really?" is the wrong question. Werner Heisenberg is young, brilliant, and suffering from hay fever. In the spring of 1925, his allergies are so severe that he takes a leave of absence from his position at the University of Göttingen. He travels to Helgoland, a small pollen-free island in the North Sea. There, alone except for his equations, he begins to think deeply about what can actually be observed in the atomic realm. Classical physics was built on the idea that you can, in principle, know everything about a system, the position and velocity of every particle. From this complete knowledge, you can predict the future with certainty. But Heisenberg realizes that in the atomic realm, we never observe positions and velocities directly. We observe spectral lines, intensities, transition frequencies, measurable quantities. What if we build a new physics based only on what we can actually measure? He begins developing a new mathematical framework. It's strange, abstract, using matrices instead of ordinary numbers. But it works. It predicts the spectral lines of atoms correctly. And hidden in this mathematics is something profound. Heisenberg discovers that certain pairs of properties can't be measured simultaneously with arbitrary precision. The more precisely you measure a particle's position, the less precisely you can know its momentum, and vice versa. This isn't a limitation of our measuring instruments. It's not that we're clumsy or our tools aren't good enough. It's a fundamental property of reality itself. A particle doesn't have a precise position and precise momentum simultaneously. These properties are complementary, mutually exclusive in a sense. This becomes known as the Heisenberg uncertainty principle. Let that sink in for a moment. A particle doesn't have a definite position and momentum at the same time. Not because we can't measure them, but because they don't exist simultaneously in nature. Heisenberg is deeply troubled by this. Years later, he'll recall walking through a park late at night, asking himself whether nature could really be as absurd as his mathematics suggested. But the mathematics doesn't lie, and experiments confirm it again and again. The clockwork universe is dead. Certainty is an illusion. At the fundamental level, reality is inherently probabilistic. You can't predict exactly where an electron will be, only the probability of finding it in various places. The future is not determined by the present, not precisely. There's always an element of fundamental randomness. This is not the comforting, predictable universe of Newton. This is something far stranger. If you think quantum mechanics can't get stranger, I have news for you. In 1935, Einstein is still troubled by quantum mechanics. He's convinced there must be something deeper, something we're missing. So he writes a paper with 2 colleagues, Boris Podolsky and Nathan Rosen. The paper is called "Can Quantum Mechanical Description of Physical Reality Be Considered Complete?" And it's intended to prove that quantum mechanics must be incomplete. The argument goes like this. Suppose you create 2 particles that interact and then fly apart in opposite directions. Quantum mechanics says that before measurement, neither particle has definite properties. They're in a superposition. But quantum mechanics also says that the particles remain correlated. If you measure one particle and find it spinning clockwise, you instantly know the other must be spinning counterclockwise, even if they're light years apart. Now, if you measure the first particle's spin, its wave function collapses and it chooses a definite spin. And instantly, the second particle must know what spin to have. But how can information travel instantaneously across space? Nothing can travel faster than light, according to Einstein's own theory of relativity. Einstein calls this spooky action at a distance. He thinks it proves that quantum mechanics is incomplete. The particles must have had definite spins all along, determined by hidden variables when they were created. Measuring one just reveals what was always there. But Niels Bohr disagrees. He argues that the two particles form a single quantum system. You can't think of them as separate entities with their own properties. Until measured, they exist in an entangled state. Measuring one instantly affects the state of the other regardless of distance. For decades, this remains a philosophical debate. Both views seem possible. Then, in 1964, a physicist named John Bell does something remarkable. He derives an inequality that distinguishes between Einstein's hidden variable theories and quantum mechanics. If Einstein is right, certain statistical correlations between measurements must obey Bell's inequality. If quantum mechanics is right, those correlations can violate the inequality. It becomes possible to test experimentally. And in the 1970s and 1980s, the experiments are performed by Elaine Aspect and others. Again and again, the results violate Bell's inequality. Einstein was wrong. Quantum mechanics is right. Entanglement is real. If you think quantum mechanics can't get stranger, I have news for you. In 1935, Einstein is still troubled by quantum mechanics. He's convinced there must be something deeper, something we're missing. So he writes a paper with two colleagues, Boris Podolsky and Nathan Rosen. The paper is called Can Quantum Mechanical Description of Physical Reality Be Considered Complete? And it's intended to prove that quantum mechanics must be incomplete. The argument goes like this. Suppose you create two particles that interact and then fly apart in opposite directions. Quantum mechanics says that before measurement, neither particle has definite properties. They're in a superposition. But quantum mechanics also says that the particles remain correlated. If you measure one particle and find it spinning clockwise, you instantly know the other must be spinning counterclockwise, even if they're light years apart. Now, if you measure the first particle's spin, its wave function collapses and it chooses a definite spin, and instantly the second particle must know what spin to have. But how can information travel instantaneously across space? Nothing can travel faster than light, according to Einstein's own theory of relativity. Einstein calls this spooky action at a distance. He thinks it proves that quantum mechanics is incomplete. The particles must have had definite spins all along, determined by hidden variables when they were created. Measuring one just reveals what was always there. But Niels Bohr disagrees. He argues that the two particles form a single quantum system. You can't think of them as separate entities with their own properties. Until measured, they exist in an entangled state. Measuring one instantly affects the state of the other regardless of distance. For decades, this remains a philosophical debate. Both views seem possible. Then, in 1964, a physicist named John Bell does something remarkable. He derives an inequality that distinguishes between Einstein's hidden variable theories and quantum mechanics. If Einstein is right, certain statistical correlations between measurements must obey Bell's inequality. If quantum mechanics is right, those correlations can violate the inequality. It becomes possible to test experimentally. And in the 1970s and 1980s, the experiments are performed by Elaine Aspect and others. Again and again, the results violate Bell's inequality. Einstein was wrong. Quantum mechanics is right. Entanglement is real. And here's another impossible thing that happens every day. Imagine you're rolling a ball toward a hill. If the ball doesn't have enough energy to reach the top, it rolls back down. It can't magically appear on the other side of the hill. In the classical world, this is obvious. Balls don't pass through solid barriers. But in the quantum world, they do. It's called quantum tunneling, and it's one of the most counterintuitive effects in physics. Remember that particles aren't really particles in the classical sense. They're described by wave functions, which represent probability distributions. When a particle encounters a barrier, its wave function doesn't stop abruptly at the barrier's edge. Some of the wave function extends into and even through the barrier. This means there's a non-zero probability of finding the particle on the other side of the barrier, even if it didn't have enough energy to go over it. The particle tunnels through. This sounds like science fiction, but it's absolutely real and has profound consequences. Quantum tunneling is why the sun shines. In the sun's core, hydrogen nuclei must fuse together to create helium, releasing energy. But hydrogen nuclei are positively charged and repel each other strongly. Classically, the sun isn't hot enough to overcome this repulsion. Hydrogen nuclei shouldn't be able to get close enough to fuse. But quantum mechanically, they can tunnel through the repulsive barrier. A small fraction of collisions result in fusion despite insufficient classical energy. Without quantum tunneling, the sun would be dark and cold. Life on Earth wouldn't exist. Quantum tunneling also explains radioactive decay. Particles inside an atomic nucleus are trapped by strong forces. Classically, they shouldn't be able to escape, but they can tunnel through the nuclear barrier, and that's why certain atoms are radioactive. It's used in technology, too. Scanning tunneling microscopes work by measuring the tunneling current between a sharp needle and a surface. This allows us to image individual atoms. Flash memory in your phone or computer uses tunneling to store data. Electrons tunnel through insulating barriers to be trapped in memory cells, or tunnel back out when the data is erased. Even the fusion reactions that power experimental fusion reactors rely on tunneling to achieve ignition at lower temperatures than would otherwise be needed. Quantum tunneling shows us that barriers in the quantum world are more like suggestions than walls. Probability leaks through. The impossible becomes merely improbable. And here's something beautiful to contemplate. There's a tiny, infinitesimally small but non-zero probability that you could quantum tunnel through a wall. It won't happen. The probability is so astronomically small that you'd have to wait longer than the age of the universe multiplied by itself countless times, but mathematically, it's not impossible. At the quantum level, nothing is absolutely forbidden, only more or less probable.
While Heisenberg is developing his matrix mechanics on a pollen-free island, another physicist is taking a very different approach. Erwin Schrödinger is Austrian, older than the other quantum pioneers, and somewhat of a romantic. He loves poetry, philosophy, and beautiful mathematics. When he reads de Broglie's thesis about matter waves, he's captivated. If particles are waves, there must be a wave equation describing them, something analogous to the classical wave equation for light or sound. In late 1925, Schrödinger retreats to a villa in the Swiss Alps with one of his mistresses. There, over the Christmas holiday, in what must have been a remarkable few weeks, he discovers his equation, the Schrödinger equation. It's beautiful. It describes how the quantum wave function evolves over time. And when you solve it for an atom, out pop Bohr's energy levels automatically. No arbitrary rules needed. The quantum behavior emerges naturally from the wave equation. Schrödinger publishes his results in early 1926. The physics community is stunned. Where Heisenberg's matrix mechanics is abstract and difficult to visualize, Schrödinger's wave mechanics feels more intuitive, more physical. But there's a problem.
What is this wave function actually waving? Schrödinger initially thinks it represents the physical spread of the electron, like a cloud of charge. But this interpretation doesn't work. The answer comes from Max Born, another German physicist. The wave function doesn't represent the particle itself. It represents probability. More precisely, the square of the wave function at any point gives the probability of finding the particle at that location if you measure it. The particle doesn't have a definite position. Instead, it exists in a superposition of all possible positions simultaneously, with different probabilities. Only when you measure it does the particle choose a location. This is profoundly weird. Before measurement, the particle is everywhere and nowhere, a cloud of possibility, a wave of potential. Only observation collapses this wave into a definite reality. Schrödinger himself becomes uncomfortable with this interpretation. He later creates his famous thought experiment with a cat in a box to show how absurd it seems. If quantum mechanics applies to everyday objects, you'd have a cat that's simultaneously alive and dead until you open the box and look. But we'll return to that cat later. For now, notice what's happening. Two brilliant physicists, Heisenberg and Schrödinger, have developed two completely different mathematical frameworks for quantum mechanics. One based on matrices, one based on waves. And here's the remarkable thing. They're mathematically equivalent. They make exactly the same predictions. They're two different ways of expressing the same underlying reality. The quantum realm can be described mathematically, but understanding what the mathematics means, what it tells us about the nature of reality, that's where things get truly mysterious. Chapter 8. The Copenhagen Interpretation and the Collapse of the Wave Function. 1 hour 35 minutes to 1 hour 50 minutes. Music becomes more thoughtful, with quiet piano. In the late 1920s, the quantum pioneers gather frequently to debate what their equations mean. The center of these discussions is Copenhagen, at Niels Bohr's Institute for Theoretical Physics. Bohr is older now, a respected elder statesman of physics. He becomes the interpreter, the philosopher of quantum mechanics. And along with Heisenberg and others, he develops what becomes known as the Copenhagen interpretation. Here are its central ideas, as strange as they may sound. First, quantum mechanics doesn't describe reality directly. It describes our knowledge about reality. The wave function represents all possible states a system could be in, weighted by probability. Second, before measurement, a quantum system doesn't have definite properties. It exists in a superposition of all possible states simultaneously, with different probabilities. Only when you measure it does the particle choose a definite position, or momentum, or energy. This is profoundly crucial. What constitutes a measurement is left somewhat vague. Somehow, when the quantum system interacts with a macroscopic measuring device or with a conscious observer, the wave function collapses. But the exact mechanism is mysterious. Einstein hates this. He finds it incomplete, unsatisfying, philosophically abhorrent. He writes letters to colleagues expressing his discomfort. In one famous letter to Max Born, he writes, "God does not play dice with the universe." Einstein believes there must be hidden variables, deeper levels of reality we haven't discovered yet. The randomness, the probability, the indeterminacy, these must be signs of our ignorance, not fundamental features of nature. But Bohr argues back. The quantum realm simply doesn't work like the everyday world. Particles don't have definite properties until measured. That's just how nature is. The debate between Einstein and Bohr becomes legendary. They argue through the late 1920s and 1930s. Einstein keeps proposing thought experiments to show that quantum mechanics must be incomplete.
Bohr keeps finding flaws in Einstein's arguments. At the Solvay Conference of 1927, Einstein suggests a hypothetical experiment involving a box of light. Bohr spends all night working through the details and points out the next morning that Einstein's own theory of general relativity proves that the experiment still obeys the uncertainty principle. Einstein, to his credit, concedes the point, but he never accepts the Copenhagen interpretation. To his dying day, he believes quantum mechanics is incomplete. Is it? Well, that's still being debated today, nearly a century later. But here's what we know for certain. Quantum mechanics works. Its predictions have been tested countless times. It's never been wrong, not once. The universe really does seem to be probabilistic at its core. Reality really does seem to depend on observation in strange ways. And we're about to see just how strange things can get. Let me tell you about the strangest experiment in physics. An experiment so bizarre that even Richard Feynman, one of the greatest physicists of the 20th century, called it the only mystery of quantum mechanics. It's called the double-slit experiment, and it's beautifully simple in concept. Take a barrier with two narrow slits in it. Shine light through the slits onto a screen behind. What do you see? You see an interference pattern, alternating bands of light and dark. This happens because light waves pass through both slits and the waves interfere with each other. Where two crests meet, you get bright light. Where a crest meets a trough, they cancel out, and you get darkness. This is exactly what you'd expect for waves. Thomas Young performed this experiment in 1801, and it was considered definitive proof that light is a wave. But remember, Einstein showed that light is also made of particles, photons. So what happens if you dim the light source so much that only one photon passes through at a time? You might expect that each photon goes through one slit or the other, like a tiny bullet. But that's not what happens. Instead, even sending one photon at a time, you still get an interference pattern. How can a single photon interfere with itself? How can it go through both slits, one slit at a time, like a classical particle? How can it go through both slits at the same time? The quantum answer is that before measurement, the photon exists in a superposition. It goes through both slits simultaneously. Its wave function spreads out, passes through both openings, and interferes with itself. Each photon lands at a single point on the screen, like a particle. But where it lands is determined by the wave interference pattern. After many photons, the pattern builds up. Now, here's where it gets truly weird. What if you try to observe which slit the photon goes through? You place a detector at one of the slits to catch photons as they pass. The moment you do this, the interference pattern disappears. Instead, you get two patches, as if each photon went through one slit or the other, like a classical particle. The act of observation changes the outcome. When you're not looking, the photon behaves like a wave, going through both slits. When you are looking, it behaves like a particle, going through one slit. It's as if the photon knows whether you're watching. This has been tested with electrons, atoms, even large molecules. The result is always the same. Observation affects the system. But what counts as observation? Does it require consciousness, or just any interaction with a measuring device?
Here's a question you might never have thought to ask. Why doesn't your hand pass through the table when you touch it? You might think it's because atoms are solid like tiny billiard balls, but that's not true. Atoms are mostly empty space. The nucleus is incredibly tiny compared to the atom's overall size. If an atom were scaled up to the size of a football stadium, the nucleus would be a grape at the center, and the electrons would be buzzing around in the outer seats. Everything in between is empty. So when you touch a table, it's almost entirely empty space touching almost entirely empty space. Why doesn't your hand pass right through? The answer lies in a principle discovered by Wolfgang Pauli in 1925, which became known as the Pauli exclusion principle. Pauli was an Austrian physicist, brilliant but notoriously critical. He was famous for his harsh evaluations of other people's work. If he thought a paper was wrong, he might say it was not even wrong, meaning it was so confused it couldn't even be evaluated. But Pauli himself made one of the most important discoveries in quantum physics. He realized that electrons are fundamentally different from photons in a crucial way. They're fermions, particles with half-integer spin, and fermions obey a special rule. No two fermions can occupy the same quantum state simultaneously. Two electrons can't have the same position, spin, and energy at the same time. They exclude each other from identical states. This is why electrons in an atom arrange themselves in shells, with specific numbers of electrons per shell. That's it. To add more electrons, you must go to a higher energy shell. This exclusion principle is why chemistry works the way it does. It's why elements have different properties. It's why the periodic table has its structure. And it's why matter is solid. When you press your hand against a table, the electrons in your hand's atoms get very close to the electrons in the table's atoms, but they can't occupy the same quantum states. The exclusion principle forces them apart, creating an effective repulsion. This is what you feel as solidity. It's not really atoms bouncing off each other like billiard balls. It's quantum states refusing to overlap. Everything you've ever touched, you've never truly touched. The electrons in your hand and the electrons in the object repel each other through the Pauli exclusion principle, keeping a tiny gap between them. You've never actually made contact with anything in your entire life. It's all been electromagnetic repulsion and quantum exclusion, creating the illusion of touch. Even as you lie in bed right now, you're not really touching the mattress. You're hovering above it on a cushion of quantum mechanical repulsion, too small to detect, but absolutely real. The solidity of the world is a quantum illusion. Chapter 13, Quantum Spin and the Electron's Strange Dance, 2 hours 46 minutes to 3 hours. Let me tell you about one of the strangest properties in quantum physics: spin. The name is misleading. It suggests that particles are literally spinning like little tops, but that's not quite right. Spin is an intrinsic property of particles, like mass or charge. All electrons have the same spin. All photons have the same spin. It's built into what they are. And spin has a very strange property. It's quantized, but not in the way you might expect. When you measure an electron's spin along any direction, you get one of two results: spin up or spin down. That's it. Never anything in between. It's like flipping a coin: heads or tails, up or down. But here's the weird part. Before you measure it, the electron spin isn't up or down, it's in a superposition of both states simultaneously. And it's not just uncertain which state it's literally in both states at once. The moment you measure the spin, the superposition collapses and you get a definite result. Now, you might think, okay, so spin is like a tiny magnet pointing in some direction, and when I measure it, I find out which direction. But no, that's not how it works. Suppose you measure an electron's spin along the vertical axis and find its spin up. Now, if the electron really had a definite spin direction all along, and you now know it's pointing up, then measuring the spin along that same vertical axis again should give the same result every time. And it does. Measure up again, you get up, both times. So far, so good. But now measure the spin along a horizontal axis. You get either left or right with 50-50 probability. Fine, let's say you get left. Now measure the vertical axis again. What do you get? You'd expect up, right? Because that's what the spin was before. But you don't. You get up or down with 50-50 probability. Measuring the spin along a different axis has somehow randomized the spin along the original axis. The spin doesn't have simultaneous values along different directions. Measuring one direction destroys information about other directions. Spin is fundamentally quantum. It has no classical analog. Yes, the name suggests something rotating, but quantum spin is stranger than anything in our everyday experience. And yet spin is crucial to everything. It determines whether a particle is a fermion or a boson. It determines magnetic properties. It's used in quantum computing as the basis for qubits. The universe runs on spin, this utterly bizarre property that defies intuitive understanding.
It's time we talked about the most famous cat in physics. Schrödinger's cat is a thought experiment devised by Erwin Schrödinger in 1935, the same year as Einstein's EPR paper. Like Einstein, Schrödinger was becoming uncomfortable with quantum mechanics, even though he'd helped create it. He wanted to show how absurd the Copenhagen interpretation becomes when applied to everyday objects. Here's the setup. Imagine a cat sealed in a box. Inside the box is a vial of poison, a radioactive atom, and a Geiger counter. If the atom decays, the Geiger counter detects it and triggers a mechanism that breaks the vial, releasing the poison and killing the cat. Radioactive decay is a quantum process. Whether the atom has decayed or not is described by a quantum superposition. Before you look, quantum mechanics says the atom is in a superposition of decayed and not decayed states. But if the atom is in a superposition, then so is everything connected to it. The Geiger counter is in a superposition of triggered and not triggered. The vial is in a superposition of broken and intact. The poison is in a superposition of released and contained. And the cat is in a superposition of alive and dead. The cat is both alive and dead simultaneously until you open the box and observe it. Only then does the wave function collapse and the cat becomes definitely alive or definitely dead. Schrödinger thought this was ridiculous. Surely the cat is either alive or dead before you look. It doesn't depend on your observation. But according to the Copenhagen interpretation, it does. Now, most physicists don't actually believe macroscopic cats exist in superpositions. There are various explanations for why quantum effects don't extend to large objects. One is decoherence. The cat is constantly interacting with air molecules, light, the walls of the box. These interactions cause the quantum superposition to rapidly collapse without any conscious observer needed. Quantum effects are fragile. They only persist in isolated systems. The more something interacts with its environment, the more it behaves classically. Another explanation is that consciousness does play a role. The cat itself is a conscious observer, or at least conscious enough. So the cat's own observation of whether it's alive collapses the wave function. The cat knows whether it's alive or dead, even if we don't. Or perhaps many worlds interpretation is correct, which we'll discuss soon. In that case, the cat really is both alive and dead, but in different branches of reality. The truth is, we don't know. The boundary between the quantum and classical worlds is still mysterious. But the thought experiment serves its purpose. It highlights the measurement problem. What counts as a measurement? When does the wave function collapse? Is there even such a thing as collapse, or is that just how we describe our limited perspective? These questions remain unanswered. But here's something beautiful. The cat, whether alive or dead, whether in superposition or not, has become immortal in another way. It lives forever in the collective imagination of anyone who's learned about quantum physics. A quantum ghost haunting the halls of science. As quantum mechanics matured, physicists realized it needed to be reconciled with special relativity. And from this marriage came something even stranger: quantum field theory. In quantum field theory, particles aren't really particles. They're excitations in fields that fill all of space. Think of space as an infinite ocean. What we call particles are waves on that ocean. An electron is a ripple in the electron field. A photon is a ripple in the electromagnetic field.
Every type of particle has its own field, and these fields exist everywhere, all the time, permeating every point in space. Even empty space isn't truly empty. It's filled with these quantum fields. And here's where it gets truly weird. These fields are never completely still. Even in their lowest energy state, they fluctuate. Quantum uncertainty prevents them from being perfectly motionless. So empty space is actually seething with quantum fluctuations. Virtual particles constantly pop into and out of existence. An electron and positron appear together, exist for the briefest moment, and annihilate each other. A photon appears and disappears. These aren't real particles in the sense that they persist and can be measured. They're virtual, but they have real effects. These quantum fluctuations contribute to the energy of empty space, creating what's called the vacuum energy or zero-point energy. They affect the behavior of real particles. The fluctuations slightly shift the energy levels of electrons in atoms, an effect called the Lamb shift, which has been measured with exquisite precision. They create a force called the Casimir effect. Place two metal plates very close together in a vacuum. The quantum fluctuations between the plates are restricted by the geometry, while the fluctuations outside have more freedom. This creates a pressure differential pushing the plates together. This has been measured. Empty space exerts force. The vacuum isn't nothing. It's a roiling sea of quantum activity. Some physicists think of vacuum energy might be related to dark energy, the mysterious force accelerating the expansion of the universe. But the calculated value of vacuum energy is spectacularly wrong, off by a factor of 10 to the 120, the worst prediction in physics. This is called the cosmological constant problem, and it remains unsolved. But the larger point stands. Even nothing is something in quantum physics. The void is never truly void. Creation and annihilation happen everywhere, constantly, on timescales too brief to notice. You are immersed right now in a sea of quantum fluctuations. Virtual particles are appearing and disappearing inside your body, in the air around you, in the fabric of space-time itself. The universe at its most fundamental level is dynamic, alive, never still. Let's talk about the future, or rather, the strange present we're living in, where quantum physics is becoming technology. Classical computers work with bits. Each bit is either 0 or 1, off or on. A string of bits encodes information. Computation is the manipulation of these bits according to logical rules. But quantum computers work with qubits, quantum bits. And a qubit can be 0 or 1, or a superposition of both simultaneously. This sounds like a small difference, but it's profound. A classical computer with 3 bits can represent one of 8 possible numbers at a time: 000, 001, 010, 011, 100, 101, 110, or 111. A quantum 3-qubit exists in a superposition of all 8 numbers simultaneously. With 300 qubits, you can represent more numbers simultaneously than there are atoms in the universe. Of course, when you measure the qubits, the superposition collapses and you get just one answer. So you can't directly access all those numbers. But during computation, before measurement, quantum algorithms can manipulate all those superposed states in parallel. It's like exploring all possible solutions to a problem at once. For certain types of problems, this provides exponential speedup over classical computers. Factoring large numbers, which is crucial for cryptography, is very hard for classical computers, but relatively easy for quantum computers using Shor's algorithm. Searching unsorted databases, simulating quantum systems, optimizing complex problems, machine learning, quantum computers promise revolutionary advances. But building quantum computers is incredibly difficult. Qubits are fragile. They must be isolated from their environment to maintain superposition. Any interaction causes decoherence, destroying the quantum state. Current quantum computers operate at temperatures near absolute zero. They're shielded from electromagnetic fields, vibrations, and cosmic rays. And they're small. The largest quantum computers have a few thousand qubits. Useful quantum computers will need millions. But progress is rapid. Companies like IBM, Google, and IonQ are building increasingly powerful machines. In 2019, Google announced quantum supremacy, performing a calculation that would take classical computers thousands of years, completed in minutes on their quantum processor. The age of quantum computing is beginning. And it's deeply strange to think that these machines work by exploiting the fundamental weirdness of reality. Superposition, entanglement, quantum interference, all the bizarre phenomena that puzzled Einstein and Bohr are now being engineered into practical devices. The quantum mysteries we've been exploring aren't just philosophical curiosities, they're becoming tools. We're learning to manipulate reality at its most fundamental level.
There's an interpretation of quantum mechanics so strange, so audacious, that when it was first proposed, most physicists dismissed it as science fiction. But it's taken seriously now by many leading quantum physicists. It's called the many worlds interpretation. It was proposed by Hugh Everett III in 1957, while he was a graduate student at Princeton. Everett looked at the measurement problem, the mystery of wave function collapse, and asked, what if the wave function never collapses? What if instead every quantum possibility actually happens, but in different branches of reality? When you measure an electron's spin and get up, there's another branch of reality where you measured it and got down. Both outcomes occur. The universe splits. Every quantum measurement, every quantum event with multiple possible outcomes, causes the universe to branch into multiple copies, one for each possibility. In one branch, Schrödinger's cat lives. In another, it dies. Both branches are equally real. In one branch, you're reading these words right now. In another branch, you decided to go to sleep 5 minutes ago. In another, you never found this video. Every possible history exists in some branch of the universal wave function. This sounds insane. It seems to violate Occam's razor, the principle that simpler explanations are better. How can it be simpler to postulate infinite universes than to accept wave function collapse? But Everett argued that it is simpler, in a mathematical sense. The many worlds interpretation requires no additional mechanism beyond the Schrödinger equation. No collapse, no mysterious interaction between quantum and classical realms, just the wave function, evolving smoothly according to quantum mechanics. Everything is quantum. The universe is a vast superposition of all possible states. What we perceive as wave function collapse is just our subjective experience of becoming entangled with one particular outcome. We don't see superpositions because we're part of them. We are split too, along with the rest of the universe. Each version of you perceives a definite outcome, unaware of the other branches where other versions of you perceived different outcomes. Is this true? We may never know. The other branches are completely inaccessible. They don't interact with ours. There's no experiment that can prove or disprove the existence of other branches. But the many worlds interpretation makes the same predictions as other interpretations. It's mathematically equivalent. So the choice between interpretations becomes philosophical. Which story do you find more satisfying? A universe where reality is fundamentally probabilistic, where outcomes are genuinely random, where observation plays a special role in creating reality? Or a universe where everything that can happen does happen, where all possibilities are realized, where determinism is restored at the cost of infinite branching realities? Both are profoundly strange. Both challenge our intuitions about existence. I find something poetic about many worlds. Every choice you've ever made, every quantum event in your body has spawned branches where things went differently. There are branches where you made different decisions, where you became a different person, where history unfolded differently. All of them equally real, equally you, living different lives in parallel. It's overwhelming and comforting at once. Everything possible exists somewhere. Every loss is accompanied by a win in another branch. Every ending is also a beginning. The universe in all its infinite richness, all its possibilities, all at once. For a long time, physicists thought quantum effects were too delicate to play any role in biology. Living systems are warm, wet, noisy environments. Quantum coherence should be destroyed almost instantly by decoherence. But in recent years, we've discovered that life has learned to harness quantum mechanics. Consider photosynthesis, the process by which plants convert sunlight into chemical energy. When a photon is absorbed by a chlorophyll molecule, it creates an excitation. An electron jumps to a higher energy state. This excitation must travel through a complex of molecules to reach the reaction center where the chemical energy conversion happens. Classical physics says the excitation should hop randomly from molecule to molecule, wasting energy and time. But experiments show that the energy transfer is nearly 100% efficient. Too efficient to be explained classically. In 2007, researchers discovered quantum coherence in photosynthetic complexes. The excitation doesn't travel along a single path. It exists in a quantum superposition of all possible paths simultaneously, exploring many routes at once. The quantum system tries every path and somehow gravitates toward the most efficient one. It's as if the excitation can sense which route is best before it actually travels. This is quantum mechanics operating in a living cell at room temperature in a complex biological environment. It shouldn't work, but it does. Birds may use quantum mechanics for navigation. Many birds can sense Earth's magnetic field and use it to migrate thousands of miles with astonishing accuracy. The leading theory involves a quantum process in the bird's eye. Certain molecules form entangled pairs of electrons when struck by light. The magnetic field affects the quantum spin states of these entangled electrons, which influences chemical reactions that send signals to the bird's brain. The bird literally sees the magnetic field through quantum entanglement. Even your sense of smell might be quantum. The traditional theory is that receptors recognize molecules by their shape, lock and key. But some researchers propose that receptors detect molecular vibrations through quantum tunneling. An electron tunnels through a molecule, and the probability depends on the molecule's vibrational frequency. Different vibrations create different smells. This is controversial, still being researched. But if true, every time you smell a flower, quantum mechanics is involved. Some scientists even speculate that quantum effects might play a role in consciousness itself. Physicist Roger Penrose and anesthesiologist Stuart Hameroff have proposed that quantum computations in microtubules inside neurons could be relevant to how consciousness arises. This is highly speculative and not widely accepted, but it's a reminder that we still don't understand consciousness, and ruling out quantum effects prematurely might be premature. The point is this: quantum mechanics isn't confined to physics laboratories. It's in the grass beneath your feet, the birds overhead, possibly in the thoughts passing through your mind right now. Life and the quantum world are not separate, they're intertwined. We are quantum beings, whether we realize it or not.
We've journeyed deep into the quantum realm tonight. We've seen its strangeness, its beauty, its power. But I want to be honest with you. Despite a century of brilliant work by thousands of physicists, we still don't understand quantum mechanics. We know how to use it. We can calculate probabilities with stunning precision. We can build technologies based on quantum effects. We can make predictions that are verified by experiment to 15 decimal places. But we don't know what it means. The measurement problem remains unsolved. What constitutes a measurement? When does the wave function collapse, if it collapses at all? What role, if any, does consciousness play? The interpretation of quantum mechanics remains contentious. Copenhagen interpretation, many worlds, pilot wave theory, consistent histories, cubism. There are numerous interpretations, each with strengths and weaknesses, none definitively proven correct. Quantum mechanics and gravity haven't been successfully unified. We have quantum field theory for the other forces, but general relativity remains stubbornly classical. All attempts to quantize gravity lead to mathematical inconsistencies.
We don't know if string theory, loop quantum gravity, or some other approach is the right path forward. We don't know why the quantum world gives way to the classical world at some scale. Where exactly is the boundary? What determines it? We don't know why quantum mechanics takes the particular mathematical form it does. Why the Schrödinger equation? Why probability amplitudes that must be squared? Why this particular structure and not something else? These are deep questions, still unanswered. And yet there's something beautiful about this. Physics hasn't ended. The universe hasn't revealed all its secrets. There are still mysteries, still questions that the brightest minds struggle with, still opportunities for someone, maybe someone listening right now, to make a breakthrough, to see something others have missed. The quantum frontier is still open. And in a strange way, I find this comforting. The universe is not a solved puzzle. It's an ongoing conversation between humanity and nature. We ask questions through experiments, nature answers in the language of mathematics, and slowly, gradually, we learn. Not everything at once, not with perfect clarity, but step by step, we illuminate the darkness. The journey of quantum physics that we've traced tonight, from Planck's desperate hypothesis to modern quantum computers, is a story of human beings refusing to accept easy answers, following the evidence wherever it leads, even when it leads to places that challenge our deepest intuitions. It's a story of courage and curiosity. And it's not over. Before we rest, let's think about what quantum mechanics means for how we understand reality. For thousands of years, philosophers debated the nature of existence. Is reality objective, existing independent of observers, or is it somehow dependent on consciousness? Quantum mechanics suggests that these questions might not have simple answers. At the quantum level, observation and reality are entangled. You cannot separate the observer from the observed. The act of measurement changes the system being measured not as a practical limitation, but as a fundamental principle. Does this mean reality depends on consciousness? Some interpretations suggest yes, others say no, that any physical interaction counts as measurement. But regardless, the old view of a mechanical universe, deterministic and independent of observation, is gone. Reality is participatory. We're not outside looking in, we're part of the system. This has profound implications for how we think about ourselves and our place in the universe. We're not separate from nature. We're nature observing itself. The universe looking back at itself through conscious eyes. Every observation you make, every measurement, every moment of awareness, you're participating in the creation of reality. Not in some mystical, vague sense, in a literal physical sense. The quantum wave function collapses under observation. Reality crystallizes from possibility into actuality through the act of witnessing. You matter. Your consciousness matters. Not because you're special or central, but because observation itself is woven into the fabric of physical law. Quantum mechanics also challenges our notions of causality. If the future is not determined by the present, if there's genuine randomness at the fundamental level, then cause and effect become more subtle concepts. Free will, determinism, the arrow of time, all these philosophical questions take on new dimensions in light of quantum mechanics. And then there's the question of identity. If the many worlds interpretation is correct, there are countless versions of you, living slightly different lives in parallel branches. Are they you? In what sense?
If your consciousness emerges from quantum processes in your brain, and those processes are probabilistic, then your thoughts, your decisions, your very sense of self are touched by quantum randomness. You are not a fixed, unchanging entity. You're a dynamic process, a pattern in the quantum foam, constantly being created and recreated, moment by moment. This could feel disturbing, or it could feel liberating. Nothing is fixed. Nothing is final. Every moment is new, emerging from the quantum substrate of reality. You're not trapped by your past. Each moment is a fresh creation, influenced by, but not entirely determined by what came before. There's freedom in uncertainty.
Let's talk about how quantum physics is shaping the world you'll wake up to. Quantum mechanics isn't just theoretical anymore. It's becoming practical, technological, transformative. We've already mentioned quantum computers, but the applications go far beyond faster calculations. Quantum sensors are being developed that can measure magnetic fields, gravity, time, and other quantities with unprecedented precision. Quantum magnetometers can detect the tiny magnetic signals produced by brain activity, potentially revolutionizing neuroscience and medical diagnostics. Quantum gravimeters can detect minute variations in Earth's gravitational field, useful for finding underground resources, monitoring volcanoes, and studying climate change. Quantum clocks are so precise they could lose less than a second over the age of the universe. These will improve GPS accuracy, enable better synchronization of financial networks, and might even detect gravitational waves. Quantum cryptography promises unbreakable security. Using the principles of quantum entanglement, two parties can share encryption keys in a way that any eavesdropping would be immediately detectable. Several companies and governments are already deploying quantum encryption networks. China has even launched satellites for quantum communication. Quantum imaging can see things that classical cameras cannot. By using entangled photons, quantum cameras can image objects with light that never actually touches them. One photon illuminates the object, while its entangled partner goes to the detector. This could enable medical imaging with less radiation, or seeing through fog and clouds. Quantum simulators will let us model complex quantum systems that are impossible to simulate on classical computers. New materials, chemical reactions, drugs, superconductors. Instead of trial and error, we'll be able to design new materials atom by atom, predicting their properties before synthesis. And all of this is just the beginning. We're at the dawn of the quantum technology revolution. The smartphones, internet, computers, GPS, medical imaging devices, all these technologies depend on quantum mechanics, whether through transistors, lasers, atomic clocks, or MRI machines. But the next generation of quantum technologies will be even more transformative. We're learning not just to observe quantum effects, but to control and manipulate individual quantum systems, to engineer entanglement, to preserve coherence, to harness superposition. The quantum world is becoming a tool. And as it does, the abstract weirdness we've discussed tonight will become part of everyday life. Future generations will grow up with quantum technologies the way you grew up with classical computers. They'll find quantum effects as natural as you find electricity. The quantum frontier is becoming the quantum homeland. As we near the end of our journey, I want to step back from the science for a moment and talk about the sheer wonder of it all. There's a poetry to quantum mechanics that goes beyond the mathematics. Think about what we've learned. That light is both wave and particle, refusing to be confined to either category. That particles exist in multiple states at once, only crystallizing into definite form when observed. That two particles can be connected across any distance, sharing a quantum state instantly. That empty space is not empty, but seething with energy and virtual particles. That the future is not determined, that uncertainty is woven into the fabric of existence. That reality is participatory, that observers and observed are inseparable.
These aren't just facts, they're invitations to see the world differently. The quantum realm teaches us that the universe is far stranger and more wondrous than our ancestors imagined, but also far more unified. Everything is connected. The boundaries we perceive are somewhat illusory. It teaches us humility. Our intuitions, evolved to navigate the everyday world, are misleading at fundamental levels. We can't trust common sense. We must follow the evidence, even to strange places. It teaches us the value of mathematics. The universe speaks in the language of math. Patterns invisible to the naked eye become clear in equations. But it also teaches us the limits of knowledge. There are questions we may never answer, mysteries that might remain forever mysterious. And that's okay. There's beauty in mystery. Not the mystery of ignorance, but the mystery of depth, the sense that there's always more to discover, always deeper to go. Quantum mechanics is like poetry in another way too. It's interpretive. Different people read it differently. Copenhagen, many worlds, pilot wave. These are different readings of the same mathematical text. Which interpretation you favor says something about your philosophical inclinations, your aesthetic preferences, what kind of universe you find meaningful. Science is supposed to be objective, but at its frontiers, it brushes against philosophy, aesthetics, even spirituality. Not that quantum mechanics proves any particular spiritual belief. It doesn't. The universe revealed by quantum mechanics is strange, but it's still physical, still natural, still governed by laws. But it's a more magical physics than anyone expected. A physics where observation matters, where possibility is real, where connections span space, where the act of measurement helps create reality. There's room for wonder here, room for awe, room to feel the mystery of existence. And you don't need to understand all the mathematics to feel it. You just need to open yourself to the strangeness, to let go of the assumption that reality should match your intuitions. The universe is under no obligation to make sense to you, but it's generous enough to reveal itself step by step to those who ask with humility and curiosity.
As I sit here in the midnight hour, thinking about quantum mechanics, I find myself reflecting on how this knowledge changes the way I experience the world. When I look at my hand, I don't just see flesh anymore. I see a cloud of quantum fields, electrons in constant motion, particles entangled with everything they've ever touched, wave functions spanning space. I see emptiness held together by forces, by quantum exclusion, by patterns of probability. When I feel the chair beneath me, I know I'm not truly touching it. I'm hovering on quantum repulsion. The solidity is a kind of illusion, or rather, a different kind of reality than I assumed. When I look at the stars, I know their light has traveled for years or centuries, each photon a quantum of energy, carrying information encoded in its frequency. And I know that the atoms in my body were forged in stars that died billions of years ago, scattered into space, drawn together by gravity, incorporated into planets, and eventually life. I am made of stardust. We all are. And not metaphorically, literally. The carbon, oxygen, nitrogen in your cells were created in stellar furnaces through quantum nuclear reactions. You are the universe looking at itself. Stardust become conscious. Atoms organized in just the right way to ponder their own existence. There's something profound in that, something that makes the problems of daily life seem smaller, less urgent. You're part of something vast, something ancient, something ongoing. The quantum fluctuations in your brain, the randomness at the heart of matter, mean that your thoughts are never entirely predictable. There's always an element of spontaneity, of genuine newness. Each moment really is